we know the equations describing the current voltage relationship of a MOS transistor. Now let's sketch those characteristics and get a better feel for what they are. Okay. And as an example, I will take a MOS transistor whose mu and Cox product is 100 microampere per volt square, and this W by L. W is some physical dimension of the transistor, L is another physical dimension, and this ratio itself is dimensionless, and this ratio I will take to be 1. So the current factor Kn, which is mu and Cox W by L, this is 100 microampere per volt square, and these dimensions do make sense because we multiply the current factor with square of the voltage to get the current. So the current factor itself has dimensions of current divided by volts squared. Okay. I will also take the threshold voltage Vt to be 1 volt. This is just for illustration in making some sketches illustrating the characteristics. Okay. Now what are the characteristics we have to sketch? The MOS transistor is a 2-port. There is the drain current ID, the gate current Ig, and each of these has to be sketched as functions of 2-port voltages, VGS gate source voltage and VDS drain source voltage. Okay. Now the gate current is 0. Okay, so there is nothing to sketch there. So we have to look for plots of ID versus VGS and ID versus VDS. Okay. Now ID versus VGS will be with some constant value of VDS, and then you can choose another constant value of VDS and then keep plotting. Similarly, ID versus VDS would be for a constant value of VGS, and then you plot it for different constant values of VGS. Okay. So let's do this. So let me take ID versus VGS. As usual, at this point I would like you to pause the video and try to sketch the characteristics yourselves, okay, for the constant values I have given, and after that you can compare it to what I draw here. Okay. So that will give you practice in doing these things correctly. So VGS, this is in volts, so let's say 1, 2, 3, 4 and so on. Okay. Now we know that when the gate source voltage is smaller than the threshold voltage, which is 1 volt, the current is 0. Okay. So the current will be 0 up to this point. So this is the threshold voltage, 1 volt. Okay. Now beyond this, the current will depend on VDS also. Okay. But if VDS happens to be more than VGS minus VT, if the transistor is in saturation region, then the curve is independent of VDS. Okay. And I will choose that case. That is, I have assumed that the transistor is in saturation region. If I choose VDS to be a very large number, this will be the case regardless of the value of VGS. This will be satisfied and the current will be independent of VDS. Okay. Just to remind you, this is also called the saturation region. So clearly for 1 volt it will be 0. For VGS equals 2 volts, this term within parenthesis will be 1 volt and this will be 1 volt square, and it will get multiplied by the current factor Kn divided by 2. So the current will be 50 microamperes. So let's say this ID is in microamperes. You can easily verify this. And similarly, if VGS is 3 volts, this number VGS minus VT whole squared will be 4 volt square. So we will get 200 microamperes, and similarly if VGS is 4 volts, this VGS minus VT whole squared will be 9 volt square, and this product will be 450 microamperes, okay, and it will keep going. And you can see that for every volt step here, the step in current is larger and larger, and that's simply a consequence of the square term over here, okay. So it will be like this. The crucial assumption here is that for all values of VGS I have shown here, I have assumed saturation, which means that VDS is greater than VGS minus VT, okay. So ID does strongly depend on VGS in this region, okay, and the slope only goes on increasing. Now what does ID versus VDS look like? Let us say this VDS is also in volts and this ID is in microamperes. It's first easy to sketch the cutoff part. That is, by the way, this plot, as you know now, I have repeated it many times, it will depend on VGS and you vary VGS as a parameter and plot this. For VGS less than VT, the current will be 0, okay. This is cutoff, okay. By the way, I should start these plots. I earlier said that I will consider VGS and VDS to be positive. So, I should start these plots from 0 and go only to the right. Next, let us take VGS more than VT. Let us take VGS of 2 volts and VT is 1 volt, right. It is easiest to plot the saturation region current, okay. When VGS is 2 volts and VT is 1 volt, we know that this expression evaluates to 50 microamperes. But it will be valid only for VDS more than VGS minus VT. And how much is VGS minus VT now? It will be 1 volt, okay. So, this will be the curve for VDS equals 1 volt. The current will be 50 microamperes. It is the same as what is evaluated here. Notice that I have made the x-axis collinear. So, this is 50 microampere and exactly the same thing is what we see over there. But this is valid only for VDS more than 1 volt, okay. So, this is the value of VGS minus VT. Next, let us take VGS equals 3 volts, okay. If VGS equals 3 volts, then this expression evaluates to 200 microamperes as we have seen here, the second point over here, but it will be valid only when VDS is greater than VGS minus VT or VDS greater than 2 volts, okay. So, in other words, for VGS equals 3 volts, we will have this constant current if VDS is more than VGS minus VT, which is 2 volts, okay. And repeating the exercise for VGS equals 4 volts, this expression evaluates to 450 microamperes, okay, exactly like here. So, this is the point for VGS equals 4 volts and that will be 450 microampere there, but of course, it is valid only for VDS more than VGS minus VT or VDS more than 3 volts, okay. So, by the way, just as an aside, I am trying to sketch these things somewhat to scale, although I am drawing it by hand, and this is a very useful thing to do. Okay. Now sketching is not very often practiced these days, it looks like, but sketching is not for accurate calculations. Okay. I mentioned this while talking about graphical analysis of nonlinear systems, but to get intuition, sketching can be extremely helpful. You make something approximately to scale and you get a very good idea of what is going on. Okay. And then you use equations to accurately calculate it. So learning to sketch curves well is actually a very useful skill in engineering. So now ID versus VDS we have drawn parts of the curves though. The question is what happens before this. Obviously this part here, let me draw some sort of a boundary. This part to the right is the saturation region where VDS is more than VGS minus VT. Now what happens before that? Before that I have to use this other equation, which is this. Okay. Now here clearly the current very much depends on VDS. Okay. In fact, you know that for VDS equal to 0, the current will be 0, right? No matter what VGS you have, VGS could be more than VT, but if VDS is 0, this entire number is 0 and the current will be 0. And that's a useful thing to remember also. Okay, the current flows between drain and source, and just like a resistor, if you have the voltage difference between drain and source to be 0, the current will be 0. The resistor of course is linear. For different values of voltage across it, the current will be proportional. In this case, the current is not proportional, but for 0 voltage across drain and source, the current will be 0. Okay. So if you think of the drain source volt difference as some sort of level difference, okay, if the difference is very small, the current will be very small, and if the difference is 0, the current will be 0. And to operate in saturation region, which is the desirable region for amplifiers, you should have a sufficient separation between drain and source. So that's some good intuitive thing to remember. Okay. Sometimes while doing algebra, especially with negative voltages and other types of transistors, you could get confused. But for every type of transistor, there has to be a sufficiently large drain to source voltage in order to have the transistor in saturation region. Okay. Now what does this curve look like? Clearly you see that there is second order dependence on VDS, which says that it's a parabola, and also the parabola, it's an inverted parabola because the square term has a negative sign. Okay. And again I urge you to evaluate this, just evaluate this parabola, you will find that it is something like that. Okay. And you can find exactly where the peak of the parabola is, the top of the inverted parabola is. Okay. It turns out that the part of the curve below this is that inverted parabola, and the peak of that inverted parabola happens to be exactly here. At that point, the current equals the saturation current. And that's not surprising. If you substitute VDS equals VGS minus VT here, this expression and this expression become the same. Okay. So the current starts from 0, then it increases with VDS in some way, and up to the point where VDS equals VGS minus VT, and after that this parabola doesn't continue. This expression is no longer valid. Okay. Then the current will be constant. Okay. So similarly for the other values, there will be some inverted parabola, the slope becomes 0 and then it stays constant, and same happens for all of them. And the region to the left side of it, this is the triode region. Notice that the boundary between triode and saturation, that's not at some fixed value of VDS. VDS itself varies depending on VGS. And this curve here in the dashed green line, that itself is a parabola. This you can easily verify. In fact, it's the same parabola as this, but shifted to 0 volts. Okay. So this should also give you a feel for first of all how to sketch the characteristics and what the MOS transistor characteristics look like. In saturation region, clearly you see no variation with VDS. So this is exactly what we wanted to have, and you have to operate it in the saturation region for the amplifier to provide a high gain. Okay. This region also has its uses. We will look at it in some later lesson. Okay. And this curve here, ID versus VGS, I have drawn it only for saturation, and it shows a sharp increase of current with voltage, and as the voltage increases it becomes sharper and sharper. And that's also apparent from the ID versus VDS curve, because when VGS jumps from 2 to 3 volts there is some increase in current, 3 to 4 volts there is a much larger increase in current, and 4 to 5 will be even larger increase, and so on. So if you draw MOS transistor characteristics for equal steps in VGS, you will see that the current steps will be unequal, they will become larger and larger. Okay. So this is what the transistors IV characteristics look like, and for amplifiers in general, you want to be here, okay, that is to the right side of this triode region, saturation region boundary, okay.